Welcome to lecture number 23 of fuzzy sets, logic and systems and applications. So, in this lecture we will discuss the complement of fuzzy sets. Although we have already discussed in one of our previous lectures the basic type of complement of fuzzy sets, but here we will discuss the complement of fuzzy sets in more detail. So, let us now take up a fuzzy set whose complement we say is a bar. So, the complement a bar is going to be obtained by operating a complement function. So, here this C, you can see here the C is such that this is going to give us, when it is operated on any membership value, we are going to get all these values in between are right from 0 to 1. So, what does this mean? This means that if we operate the C, which is a complement, which is C is a complement operator, and if this is operated on any membership value, and this membership value will be anywhere from 0 to 1, and this is going to give us again the value which is from 0 to 1 somewhere in between. So, we can say let C, which is a complement operator, is such that interval 0 to 1 is returning us the value in between 0 to 1. So, this be a mapping function that transforms the membership function of a fuzzy set A into the membership function of a complement of fuzzy set. So, here we have written membership function. So, this is applicable when we are dealing with a continuous fuzzy set, but if we are dealing with the discrete fuzzy set, then we will use the membership values or membership grades. So, we can see here that if we apply the complement operator C. So, let me write here C is the complement operator. So, C is the complement operator when this C is applied to the membership value or membership function in case of continuous fuzzy set. It is returning us mu A bar of x. This means that this is going to give us the membership value corresponding to the complement of fuzzy set, and this complement of fuzzy set is denoted as A bar. So, A bar is nothing but I will write it here, A bar is nothing but it is the complement of fuzzy set A. And what we have studied so far for the complement is the basic complement of a fuzzy set is here, like if we have membership function or membership value, and when we want to have the complement for finding the complement of a fuzzy set, we are going to simply subtract all these membership values, membership function from 1 to get the membership values or functions of the complement of fuzzy set A. So, this is simply denoted by, I will just make a box here, so that this can be clearly understood as to what is the basic fuzzy complement. So, but apart from basic complement, we have so many other complement operators. So, in order for the function C, that is the fuzzy complement, to be qualified as fuzzy complement, it should satisfy certain criteria, certain axioms. So, here we have two axioms, axiom number 1, axiom number 2, these are designated by C 1 and C 2. So, let us now look at C 1. So, C 1 says that the axiom C 1 says that if we apply the complement operator C on 0, we are going to get 1, we should be getting 1, and if we apply this complement operator to 1, we should be getting 0, and this is also called as the boundary condition. So, this is what is the axiom C 1. Now, let us now look at the C 2, axiom C 2. So, axiom C 2 says that if we have membership values mu x 1, mu x 2, and of course, these x 1 x and x 2 are from the universe of discourse, and mu x 1, mu x 2 should belong to the range 0 to 1. So, if mu of x 1 is less than or equal to mu of x 2, then the C of mu x 1 should be greater than or equal to C of mu x 2. So, C here is the complement operator. So, what does this mean? This means that the complement operator, or I would say the C is some operator. So, if this C is following these two axioms C 1, C 2, then we can say the C is a complement operator. So, for C to be called as the complement operator, the C should satisfy axiom C 1 and axiom C 2. So, if these two axioms are satisfied, we can say the operator that we are taking as C here is a complement operator. So, in other words, we can also say, as it is mentioned here, that any function C, either we say function or operator, both conveys the same meaning. So, any function C such that range 0 to 1, this is for the membership value. So, if it is applied to some membership function or membership value, which is right from the 0 up to 1, is going to be again the resulting membership value for the complement fuzzy set right from the 0 to 1. And of course, the function C should satisfy the axiom C 1 and C 2. So, this needs to be clearly understood that if we take any complement, if we take any function or any operator, say that this is a complement operator, then we need to first check the axiom C 1 and C 2, and if these two axioms are satisfied, then this function or this operator will be regarded as the complement operator. And this is going to give us the membership values or membership function for the corresponding complement of the fuzzy set that has been taken. Then we have some other complements. We have Sugeno's class of complement here, and which is written here, which is mentioned as the C lambda of mu of x, which is nothing but is equal to 1 minus mu of x over 1 plus lambda mu of x, where C lambda here is the Sugeno's complement. So, C lambda C lambda is Sugeno's complement. So, Sugeno's class of complement is C lambda of mu of x is equal to 1 minus mu of x over 1 plus lambda into mu of x, where lambda values will be in the range minus 1 to infinity. So, this has to be understood, and please understand here that since this is a complement. So, this Sugeno's class of complement is also satisfying the exams C 1 and C 2, and that is how it is regarded as, it is called as the complement operator. Now, if we take lambda is equal to 0. So, let us see what do we get. So, when we take lambda is equal to 0, the value of lambda 0, then the Sugeno's class of complement becomes the basic fuzzy complement. That is another interesting thing to note. So, here the lambda is equal to 0 means C 0. So, you can see 0 here, this is for lambda is equal to 0. This is this becomes C 0 mu x, mu of x is equal to 1 minus mu of x. So, when lambda is 0, the Sugeno's class of complement gives us the basic complement, the basic fuzzy complement that we have studied earlier. Let us take an example here to understand better the Sugeno's class of complement. So, here we have an example where we have a fuzzy set, discrete fuzzy set A as 0.7 oblique 1 plus 0.5 oblique 2 plus 0.1 oblique 3 plus 0.6 oblique 4. So, we have this fuzzy set and we need to find Sugeno's class of complement of this fuzzy set for the values which are listed here. So, values of lambda are minus 0, 0.8, 0, 1 and 2. So, let us first write the Sugeno's class of complement here, which is nothing but C lambda mu a of x is equal to 1 minus mu a of x over 1 plus lambda mu a x, which is here, and let us now quickly take the value of lambda is equal to minus 0.8, which is here, and substitute this in the expression. The expression of the C of lambda is 1 minus mu of x. If it is a, then we write here a, and then we have here 1 plus lambda mu of a x. So, when we use this, we see that we are getting for the value of lambda is equal to minus 0.8, we are getting a complement as 0.6818 oblique 1 plus 0.833 oblique 2 plus 0.9783 oblique 3 plus 0.7692 oblique 4. So, let us now see what we are getting. We have taken this fuzzy set A and here we have plotted all these values, means we have shown this discrete fuzzy set A, and let us see what we are getting as the complement of this fuzzy set A for lambda is equal to minus 0.8. So, we are getting this fuzzy set here, which is shown here as the complement of fuzzy set A, that is A bar, and this is for lambda is equal to minus 0.8. Now, let us take the another value of lambda, which is lambda is equal to 0, and let us see what we are getting. So, here we have the fuzzy set A, which was given to us, and then here the fuzzy set A, and then we have A bar here, the complement of A here for lambda is equal to 0, and we see that when we plot, we see that this is basic complement. We can clearly see that each and every membership value here of the complement fuzzy set we are getting from A by subtracting the respective membership values from 1. So, similarly, when we take the lambda is equal to 1, let us see what we are getting here. So, this is also shown here that A bar is the complement of the fuzzy set A for lambda is equal to 1. So, this is C lambda is the complement operator here, the Sugeno's complement for lambda is equal to 1 in other way we can say, and then here for lambda is equal to 2. So, we are getting the complement Sugeno's complement for lambda is equal to 2. So, this way we are getting 4 different fuzzy sets as complements, Sugeno's complements for different values of lambda. So, let us now plot all these outcomes, all these complement fuzzy sets or the complement of fuzzy set A, and when we plot membership values here, when we plot the membership values as to how they are changing with the various values of lambda is equal to minus 0.8, lambda is equal to 0, lambda is equal to 1, lambda is equal to 2. So, when we plot these membership values and its complement membership values, we see that here we have this as lambda is equal to minus 0.8 this, and this is for lambda is equal to 0, and this curve we are getting as the lambda is equal to 1, and then we are getting this as the lambda is equal to 2. So, this means what? What we are trying to relate. So, we are trying to relate here like if we increase the value of lambda, when we increase the value of lambda, we are going to get the changes like this. We can clearly see here that the relationship is changing here, the in between the membership values and its corresponding complement of membership values. Now, let us take another example here. Earlier we took the example of discrete fuzzy set. Now, we take the example of continuous fuzzy set, which is a triangular fuzzy set here, whose vertices are at 1 and 2, 2 and then 3, these 3. So, now let us find the Sugeno's complement of this fuzzy set for lambda values, and lambda values again are from this set here, and this means that lambda will take the value minus 0.8 and lambda is equal to can be again the lambda is equal to 0, lambda is equal to 1, lambda is equal to 2. So, like that let us now quickly go ahead and see what we are getting when we take the lambda is equal to minus 0.8 and what we are getting here as the complement of this fuzzy set, Sugeno's complement of this fuzzy set. So, again we have this expression for computing the Sugeno's complement of membership function, membership values, because these membership values will be needing for expressing the complement of the fuzzy set A. So, that is how we use this expression, we use this formula for computing the membership values, membership function for the complement of the fuzzy set A. So, let us now quickly see as to how we are getting it. So, we have a fuzzy set A as given, this fuzzy set is a triangular fuzzy set, and when we take lambda is equal to minus 0.8, we are getting the Sugeni's complement, you can see, and then when we take the lambda is equal to 0, the complement of this fuzzy set which is expressed by the inverted triangular membership function. So, here for lambda is equal to 0, we see that we are taking the basic complement, we are applying the basic complement, which is nothing but 1 minus mu x, means the all the corresponding membership values we get by just subtracting from highest membership value, that is 1. So, all the corresponding membership values of the complement of fuzzy set we get by just subtracting the values of the fuzzy set we are taking from 1, which we can see here. Now, similarly, we can go ahead and we can use lambda is equal to 1 and we can get the membership values accordingly, and then we can plot the A complement by taking all the respective membership values or membership function here in case of continuous, because this is continuous. So, we can use the term membership function. Similarly, for lambda is equal to 2, we are getting the A complement like this. So, we see that these the complement of the fuzzy set that we are getting for different values of lambda, we verify two axioms C 1 and C 2 for complement are satisfied. Now, here we have another class of complement, which is Jaeger's class of complement. So, Jaeger's class of complement is defined by the first of all Jaeger's class of complement, the complement operator here is C w. So, this is called Jaeger's complement, Jaeger's complement, and this is defined as C w of mu of A x is equal to 1 minus mu A of x raised to the power w, and then whole of raised to the power 1 over w. Here the w values can be anywhere in between 0 to infinity. So, or in other words we can say the w can take any value from 0 to infinity. So, from for each value of the parameter w, we obtain the complement of fuzzy set, and it is easier to check that Jaeger's class of complement satisfies the axioms C 1 and C 2 that we have just discussed. And here also if we take w is equal to 1, we are landing up in the basic fuzzy complement. So, we can see here if we take w is equal to 1, what we are getting here is the C w of mu A of x is equal to 1 minus mu A of x. So, C w becomes here, C w becomes the basic fuzzy complement operator. So, when it becomes basic complement operator, when you have w is equal to 1. So, for w is equal to 1. So, for w is equal to 1, C w becomes basic fuzzy complement operator. Now, let us understand Jaeger's class of complement better, and let us take an example and see what is happening, how these complement of this fuzzy set A look like by going through different values of W's. So, we have the fuzzy set here, the discrete fuzzy set here again. So, we have taken a discrete fuzzy set and we need to find its complement. So, as we are interested in Jaeger's complement, we have to use this, we have to use this formula. Here. So, let us now apply this formula for W is equal to 0.5, which is here, and when we apply this, we get C 0.5 is equal to 1 minus mu A of x raised to power 5 whole of raised to power 2, which is here. And this way, when we compute this finally, we are going to get this value, which is mentioned here, that is 0.0267 by 1. Similarly, other values, other corresponding values of membership for W is equal to 0.5, we get here, here. And then when we plot, we see that the complement of A for W is equal to 0.5 looks like this. Next, when we take up the W is equal to 1. So, for W is equal to 1, we apply the same formula and the complement here, complement of the fuzzy set A, we are getting as this. And since we have taken here W is equal to 1, this is returning us the basic complement. So, this is after basic, this the basic complement. So, we can clearly see that these are the basic complement. Now, when we take W is equal to 2, we are getting here A complement. Then when we plot, we are getting the A bar for W is equal to 2. Similarly, for W is equal to 3, we are getting here as the complement of fuzzy set A. So, A bar is changed here, and again when we plot, when we try to plot the membership values of the set that we have taken and then the membership value of the complement set, complement of the set A, which is here, this is complement of the set A, and yes, this has to be noted that this complement is Jaeger's class of complement or Jaeger's complement. So, when we do that, when we plot, we are going to get this kind of relationship. So, this is for W is equal to, this is for W is equal to 0.5, and then this is for W is equal to 1, and this is for this W is equal to 1, then this is for W is equal to 2, and this is for W is equal to 3. So, what does this mean? This means that when we are increasing the values of W's, we are moving towards this, and when we are, this is increasing, and I can say here that this is decreasing. So, this is how we are getting this kind of relationship in between the membership values, membership functions and its complement membership values and membership functions. Let us take another example, which is a continuous fuzzy set. Here we would like to find the Jaeger's class of complement on the continuous fuzzy set A, and we have here the W set of W's that we will be taking, and let us see what we are getting, what we are getting as the output of the Jaeger's complement of the fuzzy set A. So, let us now apply Jaeger's complement and see what we are getting. So, when we have applied, we first took the fuzzy set A, which is a continuous fuzzy set A, which is a triangular fuzzy set A, whose vertices are at 1, 2 and 3. And then when we apply W is equal to 0.5, we are getting a complement fuzzy set of A, which is like this. Similarly, when we take W is equal to 1, we get completely inverted fuzzy set, inverted of the original fuzzy set, and this is as I have already discussed that W is equal to 1 for Jaeger's class of complement is going to give us the basic complement. So, this is a basic complement, basic complement of a fuzzy set that we have taken as A. Next is for W is equal to 2, we are getting A bar like this, the complement of fuzzy set like this, the Jaeger's complement of fuzzy like this. Here also we are getting Jaeger's complement of the fuzzy set A for W is equal to 3, and this way we have seen that as to how we can manage to compute the Jaeger's class of the complement of the fuzzy set, any fuzzy set either continuous or discrete very easily. So, this way we have seen Sujeno's class of complement and Jaeger's class of complement, and we have also seen in Sujeno's class of complement for lambda is equal to 0, we are getting this operator changed to the basic fuzzy complement, and similarly in Jaeger's class of complement we have seen that for W is equal to 1, the Jaeger's complement changes to the basic fuzzy complement. So, now with this we will stop here, and in the next lecture we will discuss T norm operators on fuzzy sets. Thank you.